In this case, we had a cylindrical overrefraction with a corneal scleral. As you can see, this is the original lens to the left, and what we have is a basically spherical base curve on the back surface with a spherical front surface as well. And this is when we got our astigmatic overrefraction. To deal with the problem, we entered the overrefraction as it was measured, axis 40, and dispensed this lens. Upon dispensing, it was observed that the lens was rotating 20 degrees to the temporal position. This is a left eye, so that would be to the right. We then ordered a third lens to try to incorporate that, and what was changed was the axis of the refractive error. If we look at the results of doing that, we can see that our lens is essentially the same. The base curve is still the same all the way around because it's a spherical base curve, and our front surface is exactly the same as it was in the previous lens. So although we changed the axis of the refractive error, we did not change the lens any. To appropriately accommodate rotation of a lens, it's not the axis of the refractive error. In fact, I'll put that back to the way it was originally just for record-keeping purposes, and instead change the axis of the overrefraction. Now we apply the Lars formula: left add, right subtract. In this case, it's rotating to the right, so we would subtract 20 degrees from the axis of the overrefraction. And now if we take a look at our lens, we can see that we actually have a difference in the previous lens that had rotated and the new lens that we intend to dispense, because the axis of the astigmatism that's on the front surface of the lens that was created by the overrefraction entry has been rotated to accommodate a 20-degree temporal rotation. But that is how you address rotation, is not by changing the axis of the refractive error, but changing the axis of the overrefraction. That should help address this issue.